Then look what we did last time. We were trying to design anything. This is now a shaft design. We are the subject of shaft design. You want to write it in your note. And at the beginning, of course, it's very simple, but then it becomes a little bit more sophisticated. We go through that. This is the simple shaft. And the simple shaft, as you look, is here. We have to go through that 7-step process, yes or no, in order to decide what the size of the shaft, proper size of the shaft should be based on the tau allowable, which is 6 KSI. Remember, the summary was this, that after we go through the Morse circuit, this is the summary of what you said. I just would refresh your memory because you were not looking at this, you were looking at your previous homework. Then after we draw the Morse circuit, what do we come up with? The two numbers, maximum principal stress and maximum absolute, no, don't forget it, absolute maximum shear, which requires 3 circuits. Notice we use that idea in the beam design. We should use that idea in the shaft design. However, you will see that what happened through that system. But at the end, we calculate absolute maximum tau, and if that is less than, this is what I said at the end of class, less than tau allowable, we call that shear stress criteria, yes or no? If you look at all the homework that I selected for you, it says use the shear stress criteria. Have you seen that sentence there? No, not yet, because you haven't looked at your look at it. However, there is another one, because we don't have even, we have the tau max and we have sigma max, yes or no? Correct? What's the principal stress? Well, you are calculating the principal stress. Principal stress gives you sigma max, 2 principles, sigma principal 1 and sigma principal 2. In the ME 218, somebody said we call it maximum minimum. Here you can call it A, B, or B, whatever. But one is larger than the other one in magnitude, yes or no? So, and that one also should be less than sigma allowable, yes or no? Because otherwise my system is not safe. But this is 2 different criteria. This is what I'm saying, that one gives me sigma. Let's assume sigma P1 is larger than sigma P2, so for the sake of discussion. Therefore, sigma P1 should be less than or equal to sigma allowable. Is that correct or not? Otherwise, that's why you are going through the Morse circuit. You are going through the Morse circuit to find. First of all, where do you draw the Morse circuit? This was all in those 7 steps. Since I have to repeat the idea, I'm refreshing your memory. You go around the beam or along the shaft, you find the most critically point, yes or no? At that most critically point, you draw you don't stop at sigma x, tau x, y. Everybody understand? You draw the Morse circuit at that point to find out maximum, absolute maximum shear and absolute maximum normal stress, which are at 45 degrees to each other. Is that correct? Because of the nature of the Morse circuit. Yes, so on the Morse circuit, they were at 90 degrees. On the real problem, will be at 45. We have discussed all of that. Now we have to do the same thing for every problem, including the shaft design. Yes or no? So that 7 idea should be in front of you. We go through step by step. But the idea is this. Although it is 7 steps, as I said it at the end of class, I'm going to reduce to that all of them into 1 step. Is that correct or not? But let's see how that being achieved. You have to follow the logic behind it and write your note. Okay, first of all, there are 2 criteria. This criteria and that criteria. Is that correct? I mentioned that last time. This depends on the failure theory. Is this one fails before that one, or this one fails before that one? And why? What is the discussion? Those discussion is not going to be here. It's going to be in ME 319. When you hear your instructor, ME 319 is going to talk about failure theory, you will start it from after you draw the Morse circuit. Everybody understand that. Come up with these 2 numbers. Then we want to see which one is controlling factor, because this gives you 2 different sizes, yes or no? If you are looking for the size, if this gives me for a shaft design 1.5 quart diameter shaft, and this gives me 1 3/4. Which one is the real one? To logic tells me I should use 1 3/4, yes or no? But is this fail before that one, or that one fails before this? Because these are 2 different phenomena on 2 different planes. Everybody understand that. Maybe shear is more critical than normal stress. Everybody understand? We have not discussed that. That discussion will come later on. Anyhow, since most of our object going to be that, I selected that one. I gave you all the problem related to maximum shear stress criteria. Is that correct or not? Let's now do that for this problem. That's why you don't need the sigma allowable max. You only need tau allowable. This one I throw it in because sometimes I do the other design as well because I had time, long time ago. I do both design and then check the one against the other one. Everybody understand? In this problem, we're only going to use tau allowable equal to 6 KSI. Yes or no? Now, if I want to go through that 4th step, okay, here is the loading. You have first to do the loading. Yes or no? What loading? That means you have to change that to a shaft, yes or no? Okay, first of all, this I'm going a little bit faster because we are behind. So draw that one in your note. So you have here a shaft that, that has a bearing here at this point, at that point. And then there is a torque here going this way. There is a torque going that way. Yes or no? Yes? I put the number down because this is so simple for you guys. Here, the torque here is 24,500 times, what's the diameter of this pulley? The diameter is pulley or radius of the pulley is 12 inch, so 25 times 12. Yes or no? So let's look at that one. This is torque at D. So torque at D equal to 25, but in magnitude, it's in this direction. 25 times 12 minus 400 times 12. Yes or no? Yes? Yeah. Okay, one is plus, one is minus in this direction. So then you calculate that one, that becomes 25,200. As I said, this is the magnitude in regard to the side, but it's going this way. The other one should be the same because as you see, the other one is exactly the same, equal and opposite. So here, if you go according to your, this is what we call this one point B, C, D, E, according to that picture. Therefore, you are supposed to draw a torque diagram, X versus T, which is for this problem is mx. Is that correct or not? Then, dependent whether you want to go with the action or reaction, or when you cut it, you go to the left and right, you know, all of that changes the sign. Is that correct? So you go all action, 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 or you go reaction, reaction, reaction. Is that correct or not? The way you learned it in ME 218. The sign does not matter, so for time being, let's stick to one side or another. Let's say we go here. This is positive. The reaction here is negative. Let's go with that one. If you are negative or you go positive, I don't care. One way I show you at the end does not make any difference. But let's say that you start from here. Let's go negative reaction-wise to minus 25,200. Go from D to E. So that is D. This is B. You go to E. You add that one. Then again 0 up to C. So the torque is only between D to E. Yes or no? Now, what's the result of a stress to do that? First of all, torque is constant. You don't have to, this shaft has nothing, this part of it is safe, this part of it is safe. You have to design it for that point. Let's say take the point A, for example. At point A, the torque is constant, yes or no? What kind of a stress do we have due to this torque? This is something everybody should answer me question. What's the torque? Tau equal to what? TC over J, either plus or minus. Let's put it there. So here, as the result of this torque diagram, you get this stress, which is plus minus TC over J. Of course, TC over J. Now, in order to calculate the tau, I need the dimension. Remember, I said you have to decide on the dimension. Let's say I take 1 inch for this shaft. You have to calculate then J and everything based on that 1 inch. Yes or no? Otherwise, I cannot calculate my shear stress if I want to go. But nevertheless, no matter what size it is, this is the formula. Yes or no? Correct? Either plus or minus, depend whether it's this way, that way, depend on the system. Then you look at this, you say, oh, we now look at this one. This is not shaft only. This is a beam as well. Yes or no? Is this beam bending downward? Something we didn't consider before in ME 218 when we were talking about, because in ME 218 we were talking about each act individually, yes or no? Is this a beam? Is it going to bend downward? Should I add the stresses to this problem? Of course, yes. As you saw in your some of the tank, I asked you to calculate the stresses due to the bending. Yes? So this is also a beam. So you draw your beam action here. Now here is my problem. When I have given this type of problem to students, they know they have to put here a load. They know they have to put a load. But when they calculate the load, they say the load equal to 2,500 minus 400. Is that correct? See, still some people shaking. He said, yes. Is that correct? You said you want to get good at it. Is that correct? Yes. No. Look at the load. The load, both of them are down. So what's the total load? For the torque, one is plus, one is minus. For the load, both are downward. Don't make that silly mistake. Is that correct? I call it, because everybody knows, including you. Is that correct or not? You see, but somehow people do that mistake by looking this one, too involved in the problem. Is that correct or not? The point is, yes, it is in a way not correct, because you add the load together. You have 2,900 here, 2,900. Yes or no? Now, this beam gives you a sigma equal to what? Sigma equal to plus minus MC over I, either on top of the beam or in the shaft of the beam, bottom of the beam. Yes or no? Correct? However, there is also of course, for this one, you have to draw the shear diagram at moment diagram. By the way, since this is such a simple problem, everybody see that the reaction here is 2,900. So write it down here, 2,900. This reaction will become equal to also 2,900 pounds. These are all in pounds. Correct? And the moment, this is another mistake that students always make. When they ask you to calculate moment about here, they say 2,900 times distance. That's wrong. It's always this one. Is that correct or not? From ME 218. Is that correct? Although in this problem doesn't make any difference, but don't make that classic mistake. You should start from left, go forward like that. Is that correct or not? Yes? The moment at this point is 2,900 times this distance. Is that correct or not? Yes? So therefore, you calculate that one, and the moment becomes constant here, fortunately. So again, this is D, E, C, B. And that moment, because of that reaction, this is MZ. And that one for this problem becomes 69,600. A unit is pound inch, I believe, yes. Pound inch. Correct? Anyhow, you can calculate that by yourself. That's not the point here. The point I'm doing that is this. For this point A, which was here, I only have a sigma. I have a torque, yes or no? And I have no transfer shear. Is that correct? However, write a note for yourself. Even if you have the transfer shear in your problem, we are going to neglect that or assume it is negligible. There is a reason for it. And because the rods or shaft usually are very long, everybody understand that, and very small in cross section. Otherwise, we don't call it shaft. Is that correct or not? For that kind of problem, look what happened here. If I put here a 10-foot rod or shaft and put here, let's say, 100 pounds of load, how much moment do I have? This critical section is here, yes or no? How much moment do I have there? 1,000 pound-foot of the moment. How much shear I have there? Only 100. Is that correct or not? However, if I make similar approach to the problem like that, which I have here 1 foot, either that 10 foot, in order to create the same amount of the moment, I have to put here how much force I have to put? So the moment here and the moment here are the same, exactly. But here, there is a larger shear value. Here, there is a less shear because the distance. Everybody here, distance is larger. Force, of course, is smaller. Since force is smaller, shear value is smaller. So TC over J will give you, let's say, 7,000 PSI, 10,000 PSI. I have some example later on I'll show you. That one shows you 30 PSI or 50 PSI compared to VQ over IT I'm talking about. So since the transfer shear for this problem, write it down, cis tau equal to BQ over IT is, you put it here, negligible, compared to the other one for this type of problem. For this problem, we are not going, even if you have a shear diagram here and showing some shear, we are going to assume. So for the shaft design, we only considering the stress due to the torsion and the stress due to the bending. This is the bottom line. Write it down in your note. We are going to neglect, because it is very long. Everybody understand that, and very narrow, correct? Yes? So the amount of load become much smaller, so the transfer shear is small. Is that correct or not? Yes? This is the transfer shear is 1,000. That's the transfer shear is 100. Everybody understand it? Yes? Because of the length of the shaft. Anyhow, you will see, actually, I have some numerical example. If I get time, I will show it. It become real. Even some of the problem you did, one was about 5,000, the other one was 50 or 60. I asked you to note that. I don't know whether we did. Anyhow, so that's the point. Now, going back now to the final result is this. So regardless of the number, here I put the number. For many problems, all we are considering is this one and that one. Yes or no? Correct? Now, what will be at the end if I put now this in perspective and I drawing on top of this shaft, into top of this shaft at point A, I draw my state of stress. My state of stress, this is a state of stress that we have looked many times at it. That state of stress looks like something like that. Yes or no? Compression on top, because this is the beam or shaft. Is that correct or not? And the shear stress could go this way, that way, doesn't matter. You can draw it either way. Let's put it this way or the other way. That does not matter. This is tau equal to TC over J. This is sigma equal to plus minus, doesn't matter. You can draw it either way. Plus, I'll show you the result in a minute. This becomes plus minus MC over I. Either tension or compression. Everybody on the top of the shaft or bottom of the shaft. Is that correct? This is depend on the direction of the torque, either plus TC over J or minus. But this is in general theory. You get this and that, either plus or minus. Yes or no? Then what do you do? What was your next step? Draw the Mohr circle for this. Regardless of the number, how does it look like? This is the step one. You see, look at what I'm doing. Step one, step two, when I want to calculate sigma, I need the size, but I didn't do the size. I bypass that, come up to my stresses, the state of stress. The state of stress is somewhere between D to E. Is that correct? Because all are constant. But for this problem, between D to E, everything is constant. Look, moment end up to be constant. This is not always true. And the torque end up, look at your diagram. Torque is constant and moment is constant. That's why I choose point A. Everybody understand? Because point A, any point between C to D will do it. Is that correct or not? Yes? The same moment, the same torque. Yes?
I'm not sure. Why did you make a negative on the torque diagram?
I said it doesn't make any difference. Either going to be up or it's going to be down. This is discussion purpose. I did not say for this particular problem whether it is up or down. And you will see in a minute why. I'm saying it either go plus or could go minus. Okay. The other one, I can draw it either. I said normal stress on the top, it is compression in the top 10. I change the direction of the moment, it's going to change. Is that correct or not? So yes, you are right. Sometimes it's plus, sometimes it's, but I'm not referring to this problem. I'm putting everything there. It could be plus, it could be minus. This could not be any general more than that. Is that, I make it in general, yes or no? That's the whole purpose of coming with the one equation for that. Do you agree that this would be plus or minus? Yes? Do you agree this could be a plus or minus? However, this type of operation gives you a Mohr circle. Look at that one. For this one, I have to go negative here, yes or no? Then I have to go down, yes or no? Because this is negative yet. I have to go here. For the other one, sigma is, this is sigma versus tau. For this is a typical one format among other format. Everybody understand that. I have to draw 0 and this one. So my two xy are here, yes or no? And then when I draw the circle, look what happened. Half of circle is to the right. I get one positive, one negative. So where are the other two circles? the other circle to inside. Look, this is very important. So if I'm looking, remember I said look for absolute maximum shear stress, yes or no? But for this type of problem, which is all typical of the shaft design, you will see the other two circles both are inside, because this is your sigma z equal to sigma c equal to, that's what I was asking in your quiz to answer me, and some of you bypassed that. Some of you said, oh, I knew it, I didn't write it down. I said, how do I know that you knew it? And some of you draw all the circle, told me all about it, because I asked for absolute maximum shear. Is that, but this one, the original tau is absolute maximum, yes or no? Okay, so if that's absolute maximum shear, so that goes to R. So absolute maximum shear, I'm going backward because I'm running out of room. I hope you understand. It's going this way if you want to write it down. So what is R equal to? Tau max. Is that correct or not? Yes? Yeah. What was the equation of the tau? Everybody should more or less remember, because we always use the circle, but the equation of the tau was square root of what? Sigma x minus sigma y divided by 2 square plus what? Plus? This is something that you can pick up from the book. Is that correct or not? Now, if this is absolute maximum tau, according to my theory, this should be less than tau allowable. Yes or no? In order my shaft to be safe. If this is the most critical point, if this A happen to be most critical point, and this is its sigma in general, that's is by tau, I'm neglecting, so let's put it this way, VQ over IT, but I'm neglecting that for you to remind yourself. Is that correct or not? Yes? I'm neglecting the effect of that. This will be my maximum shear stress, and that should be less than or equal to, at the limit should be equal to sigma, tau allowable. So that is based on the checking the shear stress theory. Is that correct or not? Now let's finish this sentence. This is gone to every step, step 1 through step 7, but the only thing I have not decided yet is the size, because if I had the size, I could calculate J, I can calculate C, I can calculate tau equal to 5,000 psi. Everybody remember what I'm saying that. But I don't have the size yet because I want to simplify that. Now, tau allowable become equal to square root of sigma x. What's sigma x? This is why it does, because sigma x squared. Remember, this doesn't matter whether it is plus or minus. It becomes m squared c squared over I squared. So therefore, it becomes equal to m squared c squared divided by, this is inside. Actually, it is not like that. It is m c over 2I. Is that correct or not? Yes? The whole thing is squared. What is sigma y is equal to, look, sigma y equal to 0. I have only sigma x squared, but I have to divide it by 2. So it becomes mc over 2I squared. Plus what? Plus tau squared. Tau become what? Tc over j. T squared Tc over j squared. Is that correct or not? Now, for the circle, what is 2I? For the circle only. These are, again, things you know. What's the relationship between I and the j for the circle? 2I equal to j, yes or no? Are you using that in your homework? Because one is pi over 2, the other one is pi over 4. So I is half of j, yes or no? So 2I become, doesn't matter whether it's x or y. 2I become j. So that's why you get in this formula, this turn into, of course, it's 2I, but this also become equal to j. So then you bring this out. So you write, this is final formula. Tau allowable equal to c comes out, j comes out. This is c squared over j squared. This is c squared over j squared. Comes out, becomes c over j. What is there left is only m squared plus t squared. That's it. Yes? Did you see it, everybody there, back there? Okay, so then we write it down, j over c, which is your size. This is the size you are looking for. equal to square root of m squared plus t squared divided by tau allowable. This is the result of all 7 steps into one step. All I need is my maximum m and maximum torque. I have the size without doing any of those steps, without going through the repeat everywhere, trial and error. Look, you decide in 1 inch, you go forward with all this calculator, your tau, maximum tau comes to 2000 psi, your allowable is 6000, you have changes, this is too big, is that correct or not? You choose too small, tau become too large, is that correct or not? I explained that last time. So you have to go back and forth, keep changing the size until you get the one that makes everybody happy. Everybody happy is the balanced design, is that correct? You cannot make it too big or too small. Too small is going to break immediately, yes or no? Too big is going to be costly, correct or not? So you don't want to make a column for this building. This, of course, if you make it like Roman, we're doing a 2 meter by 2 meter, it's going to stay there. Is that correct or not? Yes, everybody understand what I'm saying that. You go further back, the design was much more, not as sophisticated as today's design. So design, everything becomes smaller and sometimes to the benefit of the manufacturer, not the benefit of the consumer. Everybody understand. You know, look at the old car and new car. Everybody see what I'm talking. Everything getting nicer, cleaner, but it becomes lighter and lighter. Yes or no? Correct, because they are using more sophisticated design today because of computer, etc. So they satisfy the authority that this is the safe design, and then use it. After a while, they say, oh, something went wrong there. It's because that happened too. Nevertheless, this is the equation. One equation answering that. Now, if I want to find the size of my shaft, what do? I don't need to worry about the Mohr circle. I don't need to worry about all of this. What criteria did I use to come to this conclusion is maximum shear stress, yes or no? All you have to say is this. This is the answer to this problem. J over C equal to square root of m squared. What's m squared? M is 69,600 square. Notice sign plus or minus doesn't matter. That's what you were asking. Do you see that? Plus minus, because everything is a square. Is that correct or not? And then plus again, because TC over J, whether it's plus or minus, doesn't make any difference. If you square it, it's still plus. Is that correct or not? Plus that one, how much is that one? 25. You plot it up, you plot it down, doesn't matter. That doesn't make, I'm not saying you should be incorrect, but if you make a mistake, doesn't matter, because this is the reference to the axis that you are choosing. Yes? And then divided by what? Divided by tau allowable. What's tau allowable is 6,000. Now the next step, of course, J is what? J is pi over 2 C to the power of 4. So you get pi over 2 C to the power of 3 equal to this number. This number, you can calculate that. So I have it here, hopefully somewhere, to show to you what happened there. So if I can find my note. Or somebody calculate that, give it to me. I know I put it here. There it is. Where are they? Here. Somewhere. Where I put it? Oh, in here. I know I have it, sorry. So that is equal to 12.33. 12.33 inch to the power of 3. Why inch to the power of 3? Because this is C to the power of 3, because it is J over, J is inch to the power of 4 divided by inch. Anyhow, you calculate the C, C become equal to 1.99 inches. Of course, you go in the market, you get a diameter of 4 inch. So that would have been the answer without any trial and, but it has gone through the Mohr circle. Everybody understand? It has gone through absolute maximum shear. It has gone through the theory of failure. Everybody understand? And we decided that here is shear criteria is more important than normal stress, yes or no? And we designed the shaft immediately, one equation. Don't be surprised when you go in the future classes, they give you a formula for the design of something, a spring in the car or something. Don't think that this is just they throw it, put it out of hat. They have put it through all this 7, this is what you were asking. All these 7 operations through the Moore circle may be simplified in this format or some other format. Everybody understand that. So we don't have to repeat and repeat ourselves. Some problem is like that. Many problems are not like that. Many problems you have to go through those steps one by one to get to the answer. Is that correct or not? Yes? All right. Now let's move on. Everybody understand that. So this is the equation you are going to use. Of course, you don't have to remember that. That equation will be given to you. Yes or no? What you need is your your torque diagram and your moment. That's it. Now let's look at another problem. So let's look at this problem next, which I put it here for your handout, the new handout. Or is it a new handout? These are some of your homework, old handout. Then I guess I have to go to the next one. So let's go to this new handout that I gave you. Last time I gave you a copy, but I put it on the computer as well. Now look at this problem. What is the difference between this problem and the one I just did? Some of you said you already have done your homework. Actually, the other class was the same. Can you see what's the difference between this problem? There is one problem which is really very little, but it is major as far as understanding of the system.
Bearings are.
Bearing is what? I'm erasing the board because I need the board. I want you to look at it and tell me what's going to happen. What?
The B, bearing B is in between the.
That's not changing the location. See, guys, look what I'm saying. That the changing of the location of the support does not. That only changes your moment diagram or the reaction, as you said, or moment diagram. Changing the location of the bearing does not change anything, but there is one major difference between this one and the other one that you can see it. Yes, there. Yes, look, this one is going downward, this one is going. So this shaft bends this way and bends this way, yes or no? You see the major difference, actually the big difference between the two, correct or not? And that's why you were doing some of the homework previously. You had MY and MZ. By the way, one more time. This is for this kind of shaft along the x-axis. This is torsion or torque. This is bending. Look at my thumb. About the z-axis. This is the bending about the double bending that we were talking about. And you have seen it in many problems as well. Now here you have to consider both of them. That's the whole design. That's the whole problem. There we left it. We said sigma A equal to that, sigma B equal to that, sigma H equal to that, sigma. Here you have to decide which point in this shaft is most critically stressed, not because of the torque, because of My and Mz. So what should I do? What did I ask you to do? The formula is the same formula. Formula doesn't change. Is that correct or not? Because that is the nature of the formula, goes through the operation. Again, you have to do 3 things this time. Here I did 2 things. Look, I draw the torque diagram and I draw the moment. This is the picture. The answer is there. That's why I want you to go through that. Here, because this is just explanation, then I do another example because I did it for other class. So I do it here too as well to show you. This is free body diagram. Yes or no? Notice there is a torque here. There is a torque here. The 2 torque are equal and everybody understand that. This is 550 times 0.05 minus 400 times 0.05. Yes or no? Torque is torque. Torque doesn't have a direction because it's round. Yes or no? This torque is how much? 300 times 0.075 minus 200 times. Also, as going this way, yes or no? This is going that way. We can call it clockwise. This is going to go counterclockwise. Yes or no? That gives you your torque diagram. There is nothing between A to C. Yes or no? There is torque is between point C and D. The value of that is either this one or that one because 2 must be equal and otherwise it is not in equilibrium. These are the things you learned in the past. Yes or no? Okay, going down this list, you will see that this is the torque diagram. Everybody see that? 7.5 going this way, 7.5 Newton meter going that way. As I said, you can consider here minus or plus, depend whether you are considering action or the reaction, left-hand side, right-hand side. Everybody understand what I'm saying? That if this is, for example, you consider this as a positive, when you cut it here, that reaction would have been negative, yes or no? So they draw this as negative. You may want to go action, action, doesn't make any difference because you are showing all the action or all the reaction, because after all, this is going to be a square. If it is a square, who cares? Is that correct or not? But this is the right format. Is that correct or not? Yes? So where should be my critical point? My critical point perhaps would be between C to D, depend on the moment diagram. Now let's go back to our loading system. Look at this load. This load is vertical, yes or no? Which gives me this beam, yes? It is a load of 950, the sum of the two, yes or no? Then you have a reaction here, Then you draw your moment diagram, which is MZ, yes or no? Correct? Now, going to the plane of X and Z, which is this horizontal plane, you have a load of how much? The load of 650, correct? And you have a reaction here going, these two reaction. Everybody see what I'm talking about? Yes or no? The reaction at the support. Where are the support? A and B, correct? Where was it, the support? Support was at here and there. Everybody see that? 150 and 650. But you have to do all of that. Everybody understand that. But then you can do that in horizontal plane, which is difficult, or you can shift it 90 degrees showing the vertical, and that's what they did here. So this is the vertical approach to the same problem. Everybody see that? This is 60-50, but they are showing vertically, but actually happening horizontally. Yes or no? Correct? Then again, this is a beam, and then it is the moment diagram for that, but this time it's not MZ, it is MY. All of this is doable by you because of what? Because you have gone through a static, you have gone through ME 218 and partially about 219, learning about MX, MY. Now we have a problem. That's the only problem we want to address. Okay, so what do I do now? Where is the point of most critical stress? I mean, where is the point of most critical stress? But is it point C? Should I use? Of course, this is such a simple problem because this is 75. The other one is 118. 118 is much larger than 75. So as you see, point C for this problem is maximum stress. Is that correct or not? Yes? However, when I put that equation, so this is what, let's go back to the equation. If I go to equation of J over C equal to square root of M squared plus T squared divided by tau allowable. Okay, here M is 118, which is the largest. Is that, do I put 118 there? No. What do I put there? Do I put, this is what the students do. Sometimes, some of them take this one, put it there. That's not a correct answer. Some of them put 118 plus 75. Neither of them are correct. 75 is max at point B. 118 is max at point C. No, look at this. I have to understand that statically. At this point, you have 0 my, you have 0 mz, 0 my, and 0 torque. The torque is down there. Is that correct or not? Yes? We are looking only between C to B because that's where our torque is. Is that correct? The torque is a constant of how much? 7.5 Newton meter. So all I need the maximum M. So this is what I'm saying you should supposed to do. In this M, you use M equal to. You did not give me the right answer. The right answer, this is 2M, My and Mz. First of all, let's look at that in general format. I explained that to you, and I tell you what we have to do. You already partially give me the answer, but we have to understand why. Let's make an imaginary system here. Let's say we have a cross-section of a shaft like this. Is that correct? Which is circle. So shaft should be circle because we did not design anything non-circular, first of all. Remember that. Anytime you see a non-circular cross-section, you know that shaft is not, the torque is not going to be involved. That's the key. Is that correct or not? Yes? All right. Let's go to the axis first. See, this usually we call the axis of the shaft, X. Then we call this one Y, and we call this one Z. Yes or no? Okay, give me an MZ. How the MZ going? Remember, MZ could be, as you said, it plus or minus. That gives you sigma plus. I said let's not worry about that for timing. This is MZ plus, yes or no? This is MZ minus. Let's assume it was plus. Is that correct or not? Just for the sake of this. If this is MZ here, exists here, that means I'm going to have compression of the top. All the blue part are the compression side. Yes or no? Yes. And all the purple side are the tension side. And everybody knows that here is 0. As I go up, increases, and I go down, increases. Yes, so remember ME218, correct? However, this is maximum for MZ. This is maximum compression, and this is maximum tension. We know, all of us know that, correct? However, this is in combination with a MY. Yes or no? Correct? Give me an MY, either plus or minus. Doesn't make any difference. Give me an MY. This is MY plus. This is the MY negative. Let's give MY plus just for the purpose of discussion. So if MY going like that, where is the compression? Here is the compression. Here is the tension. The compression were blue. So if I go blue, 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 all the way in compression side, and here tension, 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 where is maximum tension and where is maximum compression? Where do you think the max point of most critically stress is? That's what I'm asking you to do. Somewhere between where the two blues goes together. Yes or no? Most likely somewhere here. Is that correct or not? Here, so put a dot there. Because this is blue. Blue means compression and compression. This is purple or purple is tension and tension. This is one tension, one pressure, which is less than the other one. Is that correct or not? Yes? Therefore, this point is the point of maximum compression. Somewhere here, somewhere, we don't know where. This is point of maximum tension. Those have to go into my equation, correct? Can I find that location? So what should I use? What should I put into that M, first of all? This is just purely static, yes or no? Are the M are a vector, yes or no? You have this vector and that vector. How do you sum up the vector? You draw the resultant, yes or no? So what you just did here, or what you told me there were two moments. I showed the moment in black. You said this is MZ, yes or no? Look at my thumb, yes or no? And this is MY, plus, plus and plus. Then you find the resultant of that force. This is your M. This is MZ. This is My. What is M equal to? M equal to My squared plus, as you were doing all the time in a static. Very simple fact. Is that correct? But do you understand what happened? Again, that M, look interesting what happened here. That M here becomes square root of My squared plus. So look what you get here, guys. You get My squared plus Mz squared plus Mx squared. What is that? That's the magnitude of your moment vector, yes or no? Look, from static to the ME218 through ME219, we took the vector. We divided into component. Then we decided which one create bending, which one create shear stress. Then we find shear stresses, moment stresses, all of that, and then we went through the Mohr circle. At the end, for this equation, all I need, I don't care which one is torque, which one is bending. All I need is the magnitude of the moment, regardless of which one is torque, which one is ending, everybody. But that's not the way you answer your question, of course. Everybody understand what I'm saying, that I have here a item, future stress analysis. And here you have something here, and they tell you this is a moment vector. Is that correct or not? Yes? Calculate the stresses here, or that cross section, that let's say that in this cross section, I'm sorry, you have some kind of load here. You end up with a moment vector here, which is mx, my, and mz. The magnitude of that moment goes to this equation, gives you the size of the shaft. Is that correct or not? Did you see what happened? Regardless of which one is torque, which one is bending. However, another question. Can you exactly tell me with this point C and T is? That depends on the magnitude of mz and my. This is again a stat. If these two are equal, the direction is at 45, everybody. Or if this is 3 times the other one, you draw it. But the point is this. You have to be careful. This is the direction of the moment. Let me use another color. This is the vector part of it. This is red. The red is the resultant vector. Yes or no? Therefore, that one goes in that direction. This is the resultant vector, which I have to put my hand about that one. The top is compression, the bottom is tension, and that represents your neutral axis because the tension and compression cancel each other. Everybody understand along that line. Is that understood? Yes? Correct? So we have to do that for each problem. So we have to look around. Look, of course, for this problem, what do I have to do? What is my M now? Be careful. My M is not 118.75 and 75. My M is how much? 118 squared plus 37. Please put that. Many people in the final or in the quiz, they add this to that. That's wrong. This is at point C. This one is at point B. One more time, I'm making reference to that. Guys, at this point is 0, 0, 0. At that point, the torque was 7.5. This is 117, and this is 37.5 based on the ratio of this is half and half. So if this is 75, that's half. Then the half of 75 is 37.5. Everybody see that? So what goes into that equation for this problem, which you want to finish? The problem is this. J over C equal to, I'm putting in blue that you know. Here you put tau allowable. Tau allowable is given how much? Tau allowable is given 60?
50 megapascals.
50 times 10 to the power of 6. So you put it there, or just formula, you put it there. So your M is all of them together. M equal to that, which is My is 37.5 square plus 118.75 square plus 7.5. As you see, none of them is require a sign because all of them are square, so you solve for it. Is that correct? Or yes? All right. Now, let's try this one more time. Are you okay with all of this? Now, can you do this problem? Let's say this was your quiz now, guys. There are 2 more problems here. Everybody see that? I have given you some homework. Let's do this one, which is the most difficult one. Let's do this one quick. But let's go quick. Yes? I'm erasing the board. You start thinking about it. See what? Actually, it's very simple. The only thing that you have to use the
J over C.
no, that's the equation. That equation will be given to you. You don't have to remember the equation. That's the equation. You have to decide which M to use. It requires a torque diagram, 2 bending diagram. Yeah, 1 for MZ, 1 for MY. Again, X, Y, Z can change. This one, I can change this to Y and change. Actually, the original problem, believe me, this was Y and that was Z and this was X. But I changed it because I thought it will confuse you. Everybody understand what I'm saying. But I changed it to our R standard, which is this is X, this is Y, and this is Z. So the torque is MX, the bending is MY and MZ. One word. I'm sorry, MZ and MY. Is that correct? Look at my, again, one more time. MX, MZ, which is the standard one, and MY could go this way, could go that way. I don't care which way. Is that correct? Depends on the loading. Is that correct? This, you can put a load here, it bends like that. You put a load here, it bends like that. But that is MY. Everybody understand that? Putting a load here or here or here or here, that is MZ. Everybody see it. This is, look at my time. This is MZ. This is MX. And this is, look at my time. This is My and My. That's what we are talking about. You had it in lots of anytime I gave you a pipe, you had that. But we never put the 2 and 2 together, everybody, because you never were designing it. This one is the design of the shaft. You see how the things changes a little bit. Is that correct? In the design, you have to look at all the deformation there, yes or no, all the stresses. There we were looking at one at a time. Everybody understand that. Sometimes you were saying, okay, for this bending, top is compression, bottom is tension. For this bending, tension and compression, you were not the designer yet. Everybody, this is your first exposure to the design. You saw how complex the beam was. Did you see that? It wasn't just sigma equal to MC over I. We have to go through absolute maximum shear. You have to check this, you have to check that, and we end up to some conclusion. Did you see your homework? Yes or no? Then notice we had the tank in this homework, which is due Tuesday. That's why I postponed it. There are lots of material there. I have to explain all of that to you. So it was, part of it is the tank, a pressure tank. Part of it was design of beam. By now you should have done it, and you should have come to the question. Today my office hours were empty as anything that it can be, because there was no quiz. So again, Monday to Tuesday, it become very crowded because there is a quiz. That is not supposed to be. I asked you to do that extension in order for you to get a chance to do your homework ahead of time and ask all the questions that you have. Then the last part of it was the shaft design, which I partially explained, partially not. Everybody understand that? Yes? So therefore, that is, if you work on that basis, you will succeed. You'll get a better result. Let's put it this way. Okay. Now let's go to this problem. Come on. What's the torque, Evan? Can you calculate? Did you calculate the torque? 1200. Good. But it's not 1200. You need to draw the torque diagram, because you are checking different point, everybody, because depend where the bending. This is the whole idea here. I do not want, remember in the analysis, I said we need the maximum torque, maximum torque, maximum M. Didn't I say that? Oh, the maximum depends. It may happen at A, may happen at D, may happen at E. What are the maximum at that point? Is that correct? That's the whole issue here. So by saying maximum torque is 1200, you are giving me the right answer, but that's not going to help me. I need to draw it. Is that correct or not? Everybody see that? Fine. So notice that that one is very simple. When you check, I'm going to bypass that. This is 100 times 6. This is 300 times 2. And this is, of course, 300 times 4, which is 1200, 600, 600. So your torque diagram, I put it here. This is the free body diagram. This is a bearing. This is a bearing. No, the bearing is not there. The bearing is, I forgot. So let's take again. 1 second. I have it here out here. So the bearing is at, I don't know, this is very odd. The bearing is at A and at B. Okay, so this is a B. And then you have here at E, you have a torque of 1200 going that way. At D here, you have a torque of 600. And at C here, they call it C, you have a torque of 600. The unit is pound inch. Is that correct or not? Yes? So your diagram, torque diagram, going on these spaces, this is point E, this is A, B, C, D, E. So you bring those points down. So you started from either plus 100 or 600, that's up to you. Let's start with 600 plus, as I said, the sign, as long as you are consistent, it is okay. So you go 600, then add to it, and at that point, another 600, which becomes 1200. You go there, you reduce it by 1200, you get 0. Yes or no? So here is point B again. This is point E. This is very simple. You should have no problem with this one. Is that correct or not? You add this to that. This started at 600, and you cut it here is 600. You cut it here, it is 1200. Yes or no? Then you reduce it. So in other words, if this is the generator creating 1200 unit of pound inch of torque, there is a motor running here and a motor running, they're taking away. They are cutting machine, sewing machine, each one takes 50% of that. Is that correct? The balance is 0. Is that correct or not? Yes? This is how the shaft works. Is that you create the torque and somebody uses it. Is that correct or not? Yes? Well, that's your torque diagram. Most likely, now here is 600. You want to put that. This is the torque. There is a unit. You put all the unit down, pound, inch, etc., etc. And that is the log. Now you have to check where is the moment now. What the moment depends on the loading, yes or no? Now we have two loading, vertical loading and horizontal loading. You can draw this free body diagram. Sometimes they do that. They put everything in the book, which is, you can do it too. They put it everything here. They put horizontal reaction and the vertical reaction. But to me, if you do it individually, you make less mistake. Is that correct? So I treat them individually, but you can put all three of them on the same picture. Is that correct or not? This is your torque diagram. There is no reaction here. This is the action, and these two are the reaction. Is that correct or not? When it comes to the beam, you draw your beam as usual. It's very simple here. Let's look at the vertical load. Again, don't forget about point C, A, D, E, and B, the same format. Now, where is the load? The load is at D, yes or no? The load is at D, which is 300 pounds. And the reaction is at A and at B. Those are the reaction. Correct or not? Don't make a mistake, because it depends where the load is, because this one is hanging free here, as if it doesn't exist. Is that correct or not? Now, many people spend lots of time solving this problem. This is very short, because these are all single load. It's very simple. You should not spend too much time on this one. This is 12 inch, and this is 10, and this is 6 inch. You divide this based on this ratio, 16 versus 12. Everybody understand what I'm saying? Or any other way. You can take the moment about here or there, but you can do that easily. This is 175.4, and this becomes 128.6 pound, of course, both of them. Then when you do the moment, this is what I said last time. Now, many people, when they want to calculate moment at D, they say moment of D equal to 300 times 12. Is that correct? If you do that, you never learn anything about shear and moment diagram. I tell you that. That is totally inappropriate. Don't do it. Because that is external. That's the moment of 300 pounds about point A. That's what you are doing. M that we are using in ME218 is none of that. M is, you start from here, you go forward. M is 0, 0, 0, 0, 0. M is here, how much? At 1 inch. It's 171.4 times 1 inch. What's the moment here? Look at it. The moment here is 171.4 times 12 inches. That's the internal moment. This is the one that causes stress. Is that correct or not? So don't make that very bad mistake, I call it. Is that correct? But I have seen a lot of that, believe me. So therefore, start your moment diagram. Here goes up, and it goes to 0 very straight. But this is equal to 171.4 times 12. Of course, you can calculate that. I just put it there that for you to see, which become equal to that area anyway. And that becomes 2057. Again, this is, you put it here. This is your MZ. This is in pound inch of moment, and that is it, and here is 0. Now, if you need, you can calculate the moment at E, because you probably need that. But that ratio is 6/16. Everybody understand? You get this number divided by ratio of 6/16, because if it was at the middle, 8 inch, this would be half, yes or no, correct? Or multiply 128.6 by 6. Everybody understand? That is it. Is that correct or not? Either way will do it. So this number, don't spend lots of time doing that. I consider this sort of something that all of you know already. Is that correct or not? Because this is simple beam, correct? Don't make any mistakes. So this is the MZ at point A. This is MZ at point D. This is MZ at point E. And that is MZ at point, what was it? B. Okay. And this point is C. What else do I need? I need the moment about the y-axis. That's all I'm doing, that one. So I don't know where to draw that one, because they all go there, then I have to go back and forth. Do you need that one anymore? I don't think you need it. Do you? No? Okay, so let's put that one up. Here it is, so I get my file out too. So, okay, the next one is the moment about the, again, you can draw that horizontally or you can draw it that in vertical, depends on how you feel comfortable about it. So let's do vertically because this is the way you, but don't forget, I'm showing it vertically, but actually it is horizontal plane, therefore it's moment about the y-axis. Is that correct or not? Therefore, you put those points again. The same, actually, you draw this underneath each other. It's much simpler. So draw all of them, draw parallel line. I don't have room here, but therefore it becomes, so again, this is C, this is A, this is D, this is E, and that is B. And then you have a load of 100 pounds applied at point D. At point E, there is a load of 300 pounds going upward that way. At A and B are the reaction. Is that correct or not? When you do that, you calculate that one. This becomes 64.2, and that one becomes downward force of 264.2. Yeah, 64 and 64 drops out, so the result is 200. That's correct. Is that correct or not? Yes? Then you draw the moment diagram based on what I said, that the moment that's here is 100 times 12 inch. Everybody understand that? Yes or no? So you draw your moment diagram. Again, whether you draw it positive or negative, it's up to you. But since this action is positive, the reaction is negative, I'm going to go negative. Is that correct or not? So that moment become this time this distance. Is that correct or not? Then you come to this one, this time that distance minus this time that distance. Is that correct or not? So on so forth, which is very simple, or you use area method. So that goes like this. It goes like that. It goes a little bit further down, but in different slope. And then it goes to 0. This is 0. This is 0. This is at, this was A, D, where is C? C, I forgot about D. D is here. That's E, C is here. A, D, E, B. Okay, we are fine. So at point D, this is D point. This is E point, which I have to put number now down. This one is 800, because 800 times 12 inch or 800 pound foot. Or wait a minute. So that is, oh, that's 8 inch. I'm sorry. I see something. So that's, otherwise it won't be 800. And that's 8. This one is 12 inch. Is that correct? Yes. And this is 10 inches. That's 6 inches. I saw something is wrong here. So that's right. Correct. 100 times 8 is 800. Then you come to this point, moment of that, moment, minus moment of that, which comes to 1229. And then finally here become 1586. So as you see, moment diagram is not always that straight line. The other one, which was simple one, was for purpose of discussion. Yes or no? Correct? So we have this, and therefore now we are going to check. What we need to check is now very important. What do I want to know? I want to see all three of them to be the highest value. Correct? Now let's see. Where do we need to go? Do we need to go to point C? No, this is 0, this is point C. And this is 0, the other one 0, and the torque is not even 1200, the torque is 600. That's not the critical point, yes or no? Then we go to point A. Now let's check to understand. At A, this is 0, torque is 600, and that is 800. That cannot be maximum because you have much larger number there. Therefore, the critical point will be somewhere between D to E, as you see. E also is not a critical point. As you see, many zeros there. Is that correct or not? So either will be E or D. Sometimes they are too close to each other. I want you to know that. Some homework, they are so close to each other, you don't know which is which. Because if this end up instead of, I don't know, 1771, this square plus this square plus torque square maybe exists. So you have to check those 2 points to see which one is the larger. For this one, it's obvious. Which one is the larger? Is at D. Of course, you don't need to check the E because at E you have 1586 square plus 771 square. The other one, 1200 constant. I don't worry about it. So calculate like that if you want. ME total. It's 1586 square plus 771 square. You can calculate that if you want. However, MD becomes square root of this one is 1229 square MY. By the way, this was MY. And here we get 2059. Of course, the square, obviously, as you see, this is much larger than the other one because there is no trick here. Is that correct or not? They are not even close to each other. Yes? So you go to your formula. This is all you do. You put J over C, and then you put here tau allowable. But for this problem, what was tau allowable? I don't know, whatever it is, you put it there. 60? 6,000. So it is 6,000 psi. So you put that down there. And here, without any order, you can put mx square, my square, and mz square. Is that correct or not? Yes? But the way I did it, you can put it the same way here. 1229 square plus 2057 square plus 1200 square. Where is the first crack may appear if you don't make it safe? At point D. But left of the D or right of the D? See, that's not the right hand. If you say D, this is not. Because there is a, you see, whenever you have like that, you have a gear or a pulley or something there. Left of that point, D, the torque is how much? The torque is? See, right of the D, the torque is? You have to put 1200 here. Everybody understands. So the first crack or the most likely point to break in this shaft is right of D. Is that correct or not? If you make it safe here with a factor of safety of 2, everywhere else will be, of course, safe. This is how the design works. You don't just design it for every point. You don't change the column. Unless you make lots of saving, then you may want to make a column like that. It go down further down because the more weight you get, you just put it in a shape. Is that correct or not? But typically, because of the costs involved, you just use the same size for the beam and column all the way, yes? But the maximum location is the design criteria, if that's correct. The maximum, according to the Bohr circle, according to your torque diagram, and everything else is at the right of D. And where that is, still we can decide on that one. Let's go like that. Where, again, this one, because I don't have time to go to the rest of the problem. So where is mx? How much mx do I have? mx we don't have. We don't care about mx. How much mz do I have there? I have 2057 mz positive. Yes or no? So it's like that. Compression on time. Is that correct or not? So you go mz, 2057. How much y do I have there? Is at the 1229. Everybody see what I'm talking about? 1229, and that one is negative. So if it is negative, it's like that. So this is really what you put there. If those are all correct, of course, this depends whether you draw it in the right direction or not. And this will be the resultant. Is that correct or not? Yes? Based on those numbers, and you can calculate where that falls if you want to. Is that correct or not? Yes? So you know exact point, actually. If you want to put a strain gauge there to measure strain, you may want to put it there, because that's the highest point with the highest stress. Yes or no? Yes? Any other point, you have to, again, shift it through the angle. Now, for the other class, this is the end of discussion. Everybody happy with this one? Yes, except look at the last, let's just hold on one second. Look at the last homework or the previous homework. Look at the previous homework, or previous handout, I'm sorry. Look at the last problem on the previous handout. Look, it's a little ugly, yes or no? Do you have a homework like that? The other class, I asked them, Muhammad, they said no, but then I realized, yes, I have given you. The reason they said no, because they haven't checked their homework yet. Everybody, have you checked your homework? About the shaft design? Not yet? You haven't got that because you didn't know about this. Of course you couldn't. But there is a problem like that, similar to that one. Now you have to be very careful about that. All I can tell you is a few hints about something you already know. Those are the real gear system. Everybody understand that. However, you know this part, yes? this part requires loading. Is that correct or not? The only problem is that in that problem, the loading is not given, and statically, you have to come from what you know from static and what you know from ME218. You have to come with your loading. If you come with the loading, this becomes the same problem, yes or no? So there is a middle shaft. You are designing at that middle shaft. Then be careful here. If you have here a sort of gears there and a gear here, I just want to know if the two gears are on top of each other, the forces are like that, equal and opposite that. Depends where the location is. You have to consider the forces that are applied on two gears. The forces could be in this direction, or the forces could be in that direction, because the gears on top of each other, they create, depend which way they move. Is that if they move this way or it move that way? See, if the two gears are like that on top of each other, the forces here are equal, and if they are this way, they are moving that way along here, the forces are like that. Everybody, so it could be vertical or could be, remember one more time. So two gears here on top of each other create the forces in the Y direction. You learn that in a static, that these two, the forces here, you separate them, depend on the type of motion, which way you go. This force and this force are equal, and how do we get that? There is two ways. You see, in this problem, in order to get the force, you multiply the force by distance, by R, to get to the torque, yes or no? This one, usually torque will be given to you, so they tell you, okay, this is the torque amount is this much. Everybody see what I'm talking about. Then you have to look for the force. The force must be force times distance. Everybody understand that? So that is the part of it. The other part of it, that you know that the torque equal to what? A power divided by 2 pi f. Remember that equation, yes or no? Yes. In from that, yes? But power, if it is in horsepower, that's power, okay? One option, you put this in horsepower, you multiply it by what? 550 pound-foot per second. It's all in your note. It's all in your ME218 analysis, yes or no? And then F is revolution per second, not RPM. It's RPM. So you use those two ideas to calculate forces. It's reversed. So they give you the torque because you turn the engine. The engine gives you the horsepower, yes or no? Do you turn the horsepower in the torque? So you have the torque. Then you have to calculate the F. It is in reverse. Everybody understand? After you calculate the F either become horizontal or F become a vertical, which back to the problem one. Is that correct? So it's a little bit static in it. There is nothing else that I can add to it for your knowledge. Everybody understand that. You already all know that. You go to the problem there. You can figure out if it is in what system. You don't have even that one. This is 55 pound-foot per second, everybody. And this is revolution per second. So that sort of thing. So it should be easy.